Okay, so we left off doing stuff like this. So how many chiral centers does that molecule have? It has two. So it's got this one here and this one here. So there are two chiral carbons, two chiral centers. How many possible stereoisomers does this compound have? Has four, right? 2 to the n, where n is the number of chiral centers. That's going to be 2 squared, so 4. We should be able to draw all of them. Okay, so we should be able to draw all of them. And then we should be able to label each pair as either being enantiomers or diastereomers. So those two compounds, are they enantiomers or are they diastereomers? Diastereomers, right? The amine chiral center stays the same. The ethyl group changes. Those are diastereomers. Those two, diastereomers again. That pair. So these are diastereomers again, right? The ethyl stereocenter stays the same. The amine stereocenter changes. So these are diastereomers. Same over here. And there. Our enantiomers are on the diagonal this time. So I give you a molecule, you should be able to predict how many chiral centers it has, how many stereoisomers are possible, and then you should be able to draw and label all of those stereoisomers. So we're going to talk about a kind of a special type of molecule, which are meso compounds. So being chiral isn't simply the property of a carbon bonded to four different groups. It's a property that also is of molecules as a whole. So, um, um, a molecule can be chiral or achiral. So, mesocompounds are compounds with two or more chiral carbons, but that also have a plane of symmetry. These molecules are achiral because chiral things can't have a plane of symmetry. So, since there's a plane of symmetry in the molecule, it is achiral. So, what does this look like? So, let's say we had this, right? This molecule has a plane of symmetry right down the middle, right? So, this molecule is not chiral, even though it has two chiral centers. This compound is meso. An important thing to note about meso compounds is they do not have an enantiomers. Right, and this makes sense, right? If they're not chiral, they can't have an enantiomer because enantiomers only exist for chiral things. So if we were trying to draw the enantiomer of this, if we did this like we did before, where we say, hey, here's a mirror, and let's reflect our molecule across that mirror. I end up with the exact same thing, right? So I can't have an enantiomer because when I reflect it across, it ends up being the same thing. If you try to draw the enantiomer the way that where I had shown you before, where you just can switch all of the chiral centers, even though like these two molecules look different, they're the same. Right? Because if you imagine like just flipping this molecule over, just kind of grabbing it by the end and going like that, right? Everything is up will become down, and everything that's down will be up. So these OHs are pointing away from you, right? They're pointing down. When I flip it over, they're now pointing up. So they're going to be the exact same thing. So meso compounds do not have an enantiomer. So if you have a molecule with, oh my gosh, with two chiral centers, if one of the isomers is meso, only have three possible stereo isomers. Right? And this makes sense because for one of our compounds, we lose an enantiomer. We lose one of the possible stereoisomers because it doesn't have an enantiomer because it's not chiral. So if you looked at, let's say, this, right, before you put any wedges and dashes on it, right, you can say, like, I've got two chiral carbons, but I have a plane of symmetry right there. Which means I'm going to lose one of my isomers. So normally this would be 2 to the n, be 2, yep, 2 squared. So it'd be 4. But because I have that plane of symmetry, I know one of those isomers is going to be meso. So I only have 3 possible isomers. So I'll have this and that are enantiomers of one another, right? But the isomer with the two OH groups on the same side is going to be meso. It has a plane of symmetry right here. So there's no enantiomer of this compound, so I only have 3 possible isomers. So the reason that like these two compounds don't have a plane of symmetry is right? One OH is up and one OH is down. So if you go to reflect over, they miss each other, right? They don't line up perfectly. Whereas the one with the plane of symmetry, both OHs are up. So when you go to like see if everything lines up, they match. So they have to be on the same side, right? They have to be on the same side of the molecule. Because even if the groups are the same, if they don't line up perfectly, you don't have that plane of symmetry anymore. Another thing to note is um, so if you have one conformation, let's say one Newman projection is meso, it has a plane of symmetry, then we can consider all the Newman projections, all the different conformations of that molecule are going to be meso. So, for example, take this compound. Right? This compound doesn't look like it has a plane of symmetry, right? Everything's super far apart. But if I rotate around this bond, right, till my till my methyl groups line up, now I have a plane of symmetry, right? I can chop this molecule in half right here, and I have a plane of symmetry. So this compound is meso. So this conformation of this compound is meso. So all the different conformations, all the Newman projections you could draw of this compound, we just consider them to be meso. So if you can't see how I turn the molecule and got that bromine forward, right? You think I like kind of messed up the R and S. What I think is easy to do is just quickly check the R and the S. And if you've just rotated around your bond and not done anything else, you're going to see that the R and S will not have changed. So this compound is that R or is it S? It's S. So it looks like it's R, right? It looks clockwise, but the low priority group's pointing at me. So I have to switch it. So it looks R, but it is S. And then over here, I can check 1, 2, 3. Hydrogen is back 4. So this is also S. So I didn't like break any bonds or do anything like that. I just rotated around that single bond. So what that kind of looks like physically is, let's pretend these, you can see it. Let's pretend that these red carbons are our bromines, right? And the white carbons are the white groups are the carbons. So for me to have a plane of symmetry, I have to get these white groups to line up with each other. So if I turn this, right, now both of my red groups are on the same side. Right, they're both pointing away from us in this case. I flipped it the other way. Right, now my carbons line up and they're both pointing towards us. So I didn't break any bonds or anything. I just turned around this single bond, so which is kind of corresponds to the one I have the arrow around in the drawing. And you can see that your groups will move from being back to forward as you turn around that bond. So if we looked at this molecule, right? So we have this configuration, this version of this molecule, this is meso. But now this stereoisomer and this stereoisomer are enantiomers of one another. Right? So if we did the same thing, if we tried to line up the carbons to see there was a plane of symmetry, so let's say we turn around this group right here, that carbon, right? Now one bromine's forward, one bromine's back. They don't line up, so you know that there's no plane of symmetry in this molecule, so it can't be meso. So far, so good. No problem. Sure. So if you have a compound with two chiral carbons, if uh, if the four groups right on each chiral carbon match, you know one stereoisomer will be meso. So if you look at a molecule and you're like, I have two chiral carbons and the four groups on each chiral carbon are the same, then you'll know you have a meso compound. So what I mean by that is, let's say we had, right, we'll go this. If you look at this molecule, it has two chiral carbons here and here. And the groups on the chiral carbons, on both chiral carbons are the same, right? I have a chlorine, a hydrogen, and a methyl, and then whatever we would name this chain. COVID test at 12:30, right? And then I have chlorine, hydrogen, methyl, and again, that same chain. Right? So I have two chiral carbons, but all of the groups on those two chiral carbons are the same. So you know that when you start doing all of your stereoisomers, that you're going to be short one because you're going to have a meso compound. So again, if we start drawing all these out, this is just like the OHs we did earlier. Right? You have these two are enantiomers of one another, right? Non-superimposable mirror images. And then you have one isomer. I like drawing the wedges, but if you like drawing the dashes, live your life. Wait, why am I making OHs? Right? You have that, right? And if you drew this, these are the same thing, right? They're the same molecule. So I would have a set of enantiomers, and then this and this are diastereomers. Make sense? Seem good so far? They're the same thing. They're the same molecule, they're the same thing. It doesn't matter which one you drew. If you're like, I love drawing dashes, so be it. It doesn't matter because you're drawing the exact same thing that I drew if I drew the two wedges. So in a ring, only your cis isomer can be meso. So right, you have a structure, right? You look at it and you're like, okay, I know that, before I even draw my stereocenters, my wedges, and my dashes, that this molecule as drawn has a plane of symmetry. Right? So I know one of my isomers that I'm going to draw is going to have a plane of symmetry, is going to be meso. So in a ring, only the cis isomer, only the isomer where your two groups are on the same side, that's the only one that can be meso. And that's because that's the only way that everything lines up. Those OHs line up with each other perfectly. Is if they're on the same side of the molecule. When they're on opposite sides of the molecule, they don't line up anymore. It's no longer meso, or can't be meso. So far, so good. Does it all make sense? Not too terrible? Okay. So, let's say I gave you for this top pair of molecules, if we're comparing them, right, are these two molecules up here, are they enantiomers? Are they diastereomers? Are they the same because they're meso, or are they for some other reason just the same molecule? They are diastereomers, right? So you're comparing the two molecules. So this molecule here is meso, right? But we're saying this molecule compared to this one, they're diastereomers. What about the second pair? Are these enantiomers? Are they diastereomers? Or are they meso? Or are they the same thing through some other way? How many chirocarbons are there? They're the same. Why are they the same? So these are meso. How many chirocarbons does this have? Two, right? This and this. This carbon here, the gray one, isn't chiral, right? Because this group and this group are the same thing, right? So it doesn't matter if they're on wedges or dashes or not, right? So you could just look at that as being, if I just had this as, right, since that carbon's not chiral, the wedges and dashes don't mean anything. Right, so now if I drew it like that, they would be meso, right? Like, because you can just take this molecule here, flip it over, and you get exactly that molecule. Okay. Got really quiet on me for a second. Um, is that compound meso? There's a plane of symmetry that goes right through the middle of it, right there. So even though there's 4 chiral carbons, right, it's still, do I have a plane of symmetry? Does everything match up? And everything matches up. So it is meso. So this compound can't have an enantiomer. So are those 2 molecules enantiomers, diastereomers, or meso? These are meso. Right, so let's rotate, as I wrote like meat. Try again. They're meso. Right, so what if I rotate around this bond? What do I end up with? Everyone see that? Where I rotated, I took this group and I just moved it. Right, so this has a plane of symmetry. So this compound is meso. Now let me look at this one. Can I do the same thing? If I rotate the same group, and I rotate around this bond, has a plane of symmetry. And right, if I take this and flip it over, right, if I just kind of grab it and go boop, everything's going to line up perfectly. So you need to, particularly when you kind of have it is drawn in such a way that groups don't line up, right? So, you know, going back to this example, it's hard to look at this and determine if you have a plane of symmetry because your carbons are on opposite sides of that single bond, right? So it's hard to see if there is a plane of symmetry. So you need to take the time to rotate to get those carbons on the same side. So once you have those carbons on the same side, now you can actually start to see, is there symmetry? Now that I know that my carbon chain lines up and has a plane, then you can start putting your other groups in and seeing if they end up lining up. So far, so good? This went way faster than in the early section. So we're going to go a little bit in front of them. It's all right. You get bonus knowledge. So the term resolution is used when you talk about separating enantiomers, right? It's how do you resolve your enantiomers into R and S, right? You have a mixture and then you separate them. You resolve them into their components, right? And there are 2 main ways that we do this. First is via reaction. So you do a reaction and you add an extra chiral center on your molecule, and you then have diastereomers, and that allows you to separate your molecules. Or you make your chiral molecule interact with something chiral. Spell words. So you either turn your two enantiomers into two diastereomers that have different physical properties, boiling points, melting points, polarities, so you can separate them, or you have your chiral molecules interact with two different, or interact with something chiral, and they will separate themselves that way. So for number one here, right, reactions to make diastereomers, right? Let's say you have this alcohol, right, our kind of go-to stock chiral alcohol. If we did a reaction to add an extra chiral center to this molecule, let's say we were able to react with this compound here. When it reacted with this alcohol, again, don't stress. I know you don't know how this reaction works. You will one day. Today is not that day. Right, so now these two compounds are diastereomers. So now these two compounds have different physical properties, right? I could, in theory, separate these based on their boiling point. More likely, I would separate them based on the fact that one is going to be more polar than the other, right? So I would be able to separate these two compounds, but I don't want these esters, right? I want to get back to my alcohols. So to make this reaction or this kind of way to separate enantiomers work well, right, is once you have your diastereomers, we've separated them, they're hanging out in different flasks, right? This guy's up here in a flask, this guy's here. They're not mixed anymore, right? We want to get back to the alcohol. So you have to have some way to remove the ester and get back to the alcohol that you wanted. Right? Again, and they're still in their own little flasks. Right. So you do a reaction to turn your enantiomers into a mixture of diastereomers, and then you separate those through whatever means works best, and then you remove whatever group you added to make them diastereomers to get back to the enantiomers that you want. So this ends up being pretty labor intensive, right? You have to do multiple reactions to get what you want. And so there's another way that we can do this where we just take the molecules, we don't do any reactions, but we have a chiral thing for them to interact with, right? So And the thing that we do for this often is chiral separation, chromatography. Right, where we'll take our enantiomers that are mixed together. It's a terrible drawing, but you'll have to deal. You'll have a tube, for lack of a better word, that has a chiral molecule in it, right? That has chiral molecules stuck in it, usually like a sugar. And so what happens is, as your molecule goes through the chiral column, one of your enantiomers will interact more strongly with the chiral molecules in the column than the other, and it'll slow it down, right? And so then one will come through the column more quickly, and the other one will come through more slowly, and you can separate them that way. Right, so then you end up with, a flask with your one enantiomer and a flask with your other. All right, like time for like a horrific image, but here we go. Imagine, if you will, your chiral column was full of left feet. This is some saw stuff, I understand, right? And you were passing your shoes through this column, right? The left shoe fits better on the left foot, right? So it's going to spend more time on feet and not moving through the column than the right shoe will. So the right shoe would go through fast, the left shoe would go through slow because it was stuck to all those left feet, right? Your molecules, right? You have your R and your S is kind of your right hand and your left hand. If your chiral column has a molecule that interacts strongly with right-handed molecules, it's going to hold on to that molecule more tightly, and the left-handed version is going to go through more quickly. So that's basically all you're doing is you have to find a chiral column, a column that has a sugar on it or chiral molecule that interacts strongly with one of your two enantiomers, and then that will allow you to separate them uh, uh, and get the two different molecules apart.